some of the origins of the field of computing, specifically origins in mathematics, philosophy, mechanical inventions, electrical components, as well as the invention of software, which gave rise to some other fields in computing. I'll explain why there's no standard definition for the field or any of its subfields, and give a broad, although imperfect, definition of my own to describe the field. So one origin of the field of computing we can trace back is mathematics. And in mathematics, starting around the late 1890s and formalized in the 1920s, was this concept of an algorithm. An algorithm is simply a step-by-step way to solve a problem. It's a set of step-by-step instructions that someone, or in the case of a computer, something, can follow in order to solve some type of problem. And the algorithm was formalized as this step-by-step method because it was a way for mathematicians to explain to each other exactly what steps one would need to take in order to perform a particular type of computation. The algorithm is used in mathematics to solve problems mechanically, whether it be by hand or by a computer, but it's also used to apply specific rules in a mechanical and step-by-step fashion to prove that you have the correct solution to a problem. The modern concept of the algorithm did emerge by the late 1920s, and it was spurred along especially by David Hilbert's proposal of the Entscheidungsproblem in 1928, and that led to a complete formalization independently by Alan Turing and Alonzo Church within the next decade. Now, in addition to its mathematical origins, computers and computing as a field have a philosophical underpinning. And that's because internally, computer systems apply logical operations to carry out computations. Logic itself is a subfield of philosophy, largely accredited to beginning with Aristotle, who lived from 384 to 322 BC or BCE, and then continued on in more modern times, relatively speaking, by Charles Babbage, Augustus de Morgan, George Boole, and Gottlob Frege. Mechanically, some of these same philosophers, as well as others, began to develop machines to perform calculations automatically. These machines were invented as a tool. They were invented as a convenience and as a way of performing more of these calculations more quickly. The ancient Babylonians, for example, developed the abacus back in 2400 BC, BCE, or thereabouts, and the abacus was widely used up through Roman times and even well into relatively modern times before the invention of the calculator. Blaise Pascal developed the first mechanical calculator back in 1642, and Charles Babbage attempted to develop a more precise, more capable machine called the difference engine in 1822. Metalworking at the time, however, meant that in 1822 there simply wasn't the metal crafting technology to build a device precise enough to implement the difference engine, and so the difference engine never quite fully worked. The earliest impetus, or one of the earliest impetuses for what we think of as modern computing, really came about as a result of cryptography. Arthur Scherbius, in 1918, patented a device that would later be known as the Enigma machine, which was used by the Germans during World War II as a mechanism for encrypting messages sent within government and military organizations. In order to gain insight into the contents of these messages and to gain intelligence and predict the movements of German Army and Navy and air operations, the British commissioned the development of their own mechanical devices. And these were electromechanical devices because they were spun by electric motors. Alan Turing led the creation of one of these first devices on the British side, which was called the bomb, in 1939, and this device was specifically designed for the purpose of de-encrypting messages sent that were encrypted with the Enigma machine. So the idea here was to break the Enigma encryption and gain intelligence during the war. Electrically, as early as 1935, a Soviet scientist by the name of Viktor Shestakov demonstrated the correspondence between electrical circuits and logical operations, and demonstrated by connecting different vacuum tubes together that certain logical operations could be implemented entirely electrically without the use of mechanical components. Claude Shannon independently discovered this and actually published these results first in 1937. And as a result, his terminology, logic gates, became the standard terminology to describe these types of electrical circuits. The first fully programmable, fully digital electrical computer that was not an electromechanical computer was developed in 1943, also by the British, for the purpose of code breaking. This was called Colossus. That was followed 3 years later with the ENIAC, which was the first general-purpose digital computer. In 1947, John Bardeen, Walter Brattain, and William Shockley developed the transistor, and the transistor proved to be a much more economical replacement for the vacuum tube and allowed computer hardware to develop at increasingly exponentially fast rates. One thing that these early programmable systems gave rise to was this idea of software. Software is a component of the computer system that is intangible. So computer hardware consists of devices. It consists of contraptions that are built and assembled that you can hold in your hand. Software isn't like that. Software cannot be held in your hand. In modern computers, software is stored on the computer itself. It is a set of instructions that the computer follows as it executes its operation. It's easier to change software compared to changing hardware, and so software implementations of different technologies are typically more economical than dedicated hardware implementations of the same technology. But software itself is pretty complicated, and as a result, it's given rise to fields that are entirely devoted to software and nothing else. Computer programming, for example, is the focus of actually creating the software without really dealing with the hardware. Software engineering is the idea of developing software applications to fit specific purposes. In other words, to take user requirements, to take requirements expressed in a different field, be it business or science or some other field, and actually come up with designs for software that can be programmed to solve the problems that are proposed by those fields. Now, computing itself is a young discipline. The first programs in computer science didn't come about until the middle of the 20th century. The University of Cambridge in England started offering a computer science diploma in 1953. In the United States, it wasn't until 1962 that Purdue University started offering the first bachelor's degree in computer science. The first bachelor's degree in computer engineering emerged in 1972, a full decade later, at Case Western Reserve University, also in the United States. So this entire field, formally in an academic sense, is only about a generation old. Some subfields within this field, like information systems and information technology, can be traced back to the 1980s and 1990s. These are within my lifetime. Human-centered computing and other fields within the broader field of computing didn't come into existence until the 2000s, and more fields are emerging even today. So computing is an extremely young discipline, and it's an extremely dynamic discipline. Unfortunately, as a result of its youth, the discipline has led to a whole bunch of disagreements within the field and within its subfields, and as a result, there is no accepted universal standard definition for most computing fields. For example, the field of computer science is still not precisely defined. Is the field of computer science broad? Does it include software development? Or is it narrow? Is it focused strictly on the mathematical operations of the algorithms underlying computation? One of the earliest contributors to the idea of how computer science should be taught was a gentleman by the name of Edgar Dijkstra, and he argued that computer science was about the study of algorithms, was about the study of mathematics, and had actually nothing to do whatsoever with the computers themselves. So much so that he himself refused to use a computer. He wrote everything that he wrote during his lifetime by hand and let somebody else type it. He also argued that the field of software engineering shouldn't even exist. So Dijkstra had some strong opinions in this direction, and there are some folks today who follow Dijkstra's philosophy that computer science is really all about the mathematics behind computing. Of course, there are plenty of other people, myself included, who do not subscribe to that philosophy and who see computer science as broader than simple study of algorithms. Information systems grew out of the 1980s and the idea that somehow we need to be able to apply these computing systems to business. In the 1980s especially, most businesses became fully computerized and changed tasks that were performed by hand into tasks that would be performed computationally. The idea of translating business requirements into workable computer systems gave rise to this idea of information systems as a separate subdiscipline within this broader field of computing, or a separate discipline if you disagree that a broad field of computing even exists. Information technology is also a relatively recent invention. Dates back to when computers first became miniaturized enough, turned into what we call microcomputers, or just computers these days, that businesses and eventually individuals had their own. The earliest computer systems required entire buildings complete with dedicated air conditioning systems just to operate. Compare that with a modern computer that you can hold in your hand. All of these things happened within the span of about 30 years, and the idea of a small personal computer that emerged in the late 1980s. So information technology deals with, in one sense, managing all of these different computing devices. However, in business speak, information technology might also include programming these devices. So does information technology include, in a broader sense, what we call computer science, or information systems in a narrower sense? And some people would argue that yes, it does, and other people would argue that no, it doesn't. It's a separate subfield. Computer engineering grew out of electrical engineering and deals primarily, in many places at least, with the actual development of computational circuits, as well as processing signals and determining how the circuit should be implemented. But some universities, computer engineering actually includes software engineering, which doesn't deal with hardware much at all. It deals mostly with software and how software applications are developed. So, should computer engineering include software engineering? There are disagreements about this, and so on and so forth. Just about everything in the field has disagreements. These disagreements are driven in large part by university politics, since the field of computing and its broader areas are driven partly by industry, but the way we define what belongs in what area is often driven by academia. And in academia, the differences between fields are often the result of internal politics. For example, the canonical example is computer science versus computer engineering. Computer science existed as a separate discipline first, by 10 years. Computer engineering is the younger of the two. But at many universities, computer engineers act like they are superior to computer scientists and have this mentality that computer engineering should really take over all the things that computer science does. Some of this is driven by the fact that in many of these universities, computer engineering is part of the electrical engineering department, whereas in many universities, computer science has its own department. And in some universities, computer science is part of mathematics, but in many, it's its own department. This comes straight down to the issue of funding. Within the university system, most funding is allocated on a per department basis, not a per program basis. Therefore, there's some disagreements here, in part because one discipline managed to get its own funding, its own department, whereas another discipline is often launched in with another department, in the case of computer engineering with the electrical engineering group, and so there'll be internal frictions between electrical engineering and computer engineering about how to spend the money. Of course, in computer science, there's similar internal frictions between members of computer science departments. So, in the bigger sense, these disagreements are universal, and the types of nonsensical stuff that gets promulgated by people in these departments is absolutely crazy. For example, there's a belief among computer engineers in a lot of computer engineering disciplines that a computer engineer could do anything a computer scientist could do, or anything that an information systems person could do. Well, I understand these low-level details about how the hardware works, therefore I'm qualified to go out and work with somebody in the business field to develop a software solution that solves their particular needs. And in many cases, this really isn't true. There's also a perception, and this perception does exist at Coastal Carolina University, that information systems is somehow an easier discipline than computer science. This is also nonsensical because it's not possible to compare these two things, at least the way we have them defined at Coastal Carolina University, because they're really completely different subfields that just happen to be in the same department. In fact, what I find in academia is that which discipline is quote-unquote harder or quote-unquote easier has more to do with the personalities of the faculty members teaching within those disciplines and their own approaches to grading than it does with whether the discipline itself is easier or harder. So making statements, blanket statements like this, it's common in our field, but I would encourage you not to subscribe to any of them. So, what do I call the field of computing? Murphy's definition of computing. This is broad, and that is that computing is the study of programmable devices, their means of operation, their applications, their impacts on society, the planet, space, and beyond. So this is a nice pie-in-the-sky definition that immediately kicks the can into asking, well, what do you consider to be a programmable device? And my answer to that question is simply a device that acquires some or all of its function from software that's stored on that device. It doesn't imply you can change that software if you're an end user of the device. It just implies that the device is partly implemented using software. Of course, this is an imperfect definition. If the device requires software, okay, great, precisely defined software. Well, that's somewhat easy to do if we consider only our current state of computing. We can differentiate hardware and software fairly easily. When we start talking about quantum computing, when we start talking about some newer techniques that we might use for computing in the future, this definition might actually get kind of hard to apply. Similarly, the impact of computing on society and the planet is all well and good, but if we discover that we're not alone in the universe and that there are aliens out there somewhere who might have independently developed computing systems, our understanding of those impacts might not be quite in line with their understanding of those impacts. So it's not a perfect definition, but the idea here is to capture the breadth of it. Anything dealing with programmable devices, that's what I consider to be computing. There are all kinds of different subspecialties within this broader field. These subspecialties are frequently at war with each other, figuratively and sometimes literally, because they disagree about whose is better and whose is more important. All of these disagreements are downright silly, but they do them. And so computing is just sort of this umbrella term for housing a lot of different people who don't always get along with each other. So in summary, computing, as I'm defining it, is a broad field. It has evolved from a number of different areas, including mathematics, philosophy, mechanics, and electronics, but not limited to those areas. Other fields have made contributions to the field of computing. Biology, for example, has made contributions to the field of computing. Ecology, different sciences have contributed to the field. So we can't limit it to just those four, It's just it would be an entire class talking about the origins of computing, and this is one lecture going on about 20 minutes now. All disciplines within the field of computing are young. They're less than 70 years old. My parents have been alive throughout have been alive throughout the entire existence of the fields of computer science and information systems, at least during the United States. Some of the fields have been invented in my lifetime, and some of these fields have been invented while I was in graduate school, human-centered computing, for example. So these disciplines are young. We're still working out what they are, what they're not, and there are a lot of disagreements within the field about what they are and what they're not, and what they are not. But many of these disagreements actually have political origins that, sadly enough, can be traced to funding issues. So, broad field, we're focusing on programmable devices and studying those devices and their applications.